All right then. Hello and welcome back, everyone. Happy Friday. Um, so today's EMP session, we're going to talk about linked lists. We're going to do some algorithm analysis, and we're going to also look at maps, not exceptions. So this is a typo here, but we'll look at maps after this. And So the linked list stuff is going to be a little bit more challenging than usual, and it's not likely to be something that we'll ever test you on in 125. But a lot of people requested linked lists, so that's why I threw this in there. Um, and then I think the algorithm analysis will hopefully get you guys more familiar with the whole concepts of how to um, come up with big O notation. We've been doing it for a few sessions now, so this should hopefully be like a review, but if not, that's okay. Okay, let's take a look at the linked list stuff. All right. So, like I said before, this linked list stuff is not going to be something we're testing you on. And that is because we're going to be looking at cyclical linked lists today. And cyclical linked lists are more complicated versions of the singly linked lists that you guys have been looking at. The only difference though is that the last item doesn't have like a null reference at the end, but it actually references the very start of the linked list. So as you can imagine then, it, it looks a lot like a circle or a cycle. Um, So let's kind of look at the difference visually, and then we'll do an example problem. Okay, so this is a regular linked list that most of you are probably familiar with at this point. Um, that you got the new linked list, and it points to some start value that you can keep track of, and then the start values next points to another value, so on and so forth. But the last item in the linked list always points to null. So this is what we're going to be changing right here. We're going to take this off, and then we're going to have it point to the very beginning. Okay. So let's take a look at that. Yeah, so this next value will now point back to the start value of the linked list. And that is the critical piece here. All right. So next, I think, is going to be the problem. If this is understandable to you, then great. We'll go ahead and jump right into it. If not, let me know, and I can explain a little bit more. But the idea, I think, is kind of intuitive, especially if you see on the screen. What's more difficult here, though, is going to be looping through this linked list now, because before we were relying on this null character to tell us where the end was, but now we have to think about what do we need to do to know where the end of the quote unquote end of the linked list is, right? And the way you can do that actually is, so remember that in our traditional implementation of linked lists, we always have a start node that we're defining. But now in the cyclical linked list, we can also keep track of the last node in the linked list. So this would be the start node, and then this one would be the last node. So if you keep track of both of them, you know that if you end up looping through the linked list and you end up in a point where you're pointing back at the start node, then you've reached the end of the linked list. So that's one way to utilize this implementation so that you know where to end. Okay, so here is the linked list problem statement. So we're going to give you some starter code on the next slide, and it'll guide you through this. So use it. I think it'll really help you. But your goal here is to write two functions. One is to convert it into a cycle. So we talked about um, what it means to be a cycle, right? So what kind of code changes you have to make here in order for this to be a cycle. So one thing remember for that part is that the end of the linked list will no longer point to null. Now we have to figure out what the last node is and how do you point to the last node at all times. So when you add a new item, you have to make sure that the last node updates. When you're printing out the linked list, you have to make sure you know where to end. So that's going to be your first task, implementing this cyclical linked list and making modifications here in the start of the code on how you need to do that. And I'll actually give you some tips because I know it's going to be a little difficult. And then the second part of it is that you have to convert the linked list cycle into a string, which we already do for you here. But what you're going to do a little bit differently, though, is you're going to this function is going to take in an integer n and it'll print out the cycle n times. So if your linked list has 3 items in it, it needs to print out those 3 items n times. So that is kind of the first task for this morning. So let's do 15 minutes for this implementation of a cycle. And then let me just give you some pointers on this part. So in order to fully implement the cycle, you're going to want to make 2 major changes. One is you're going to have some way of keeping track of the end of the linked list, just like we have some way of keeping track of the start. So make the necessary changes here inside of the linked list implementation to keep track of the end of the linked list. Then the other piece of it is this add method, right? When we're adding a new item into the linked list, we have to ensure that we're also making changes to the last as well as the start. Last node as well as the start node. So those are the 2 things you can keep in mind. And then we've got some test cases here on the next slide that you can use to see if your cyclical linked list is working as it should be. Okay, great. So that is the linked list problem. I'm gonna stop talking now and you guys can work for 15 minutes. If we want to do a hint at like 7 minutes, we can. Just give me a heads up. If not, and you want to give this a shot kind of on your own, then that's fine too. So let's regroup at 6:30. And just DM me if you finish everything or if you're stuck. Good luck. Okay, so it's 6:31 actually. So let's go ahead and look at the code and how you'd implement this. So right off the bat here, keep in mind that we don't expect you guys to be able to do this ever on a quiz, and so we don't expect you guys to have completed this in this amount of time. So don't beat yourself about it if you didn't. Um, this is more of like an interview style question, and at the best case, you'll be ready for a technical interview. Worst case, you know how hard link lists are. So what I did here is I just copied and pasted the starter code over to the playground, and then I just copied and pasted this test case down here at the bottom of my linked list implementation. Okay, so here, let's first think about what changes we need to make. So I'm going to want to have some way of keeping track of the end of the linked list, right? Like I mentioned before, we have the start and we have the end. And that's just because you wouldn't know where to end if you didn't have some way of keeping track of both of these things. Um, and then kind of the critical piece after that is this kind of here, you could say this dot end. So if you had like a linked list constructor that was kind of the default constructor, meaning it didn't have anything inside of it, what would you want that to do? You would want that to, if it's starting off with start equals to null, and this dot length is equal to 0, you might want to set this dot end equal to null also, because it's kind of an empty linked list at this point. Then we don't have to make any changes to the item class because the item class really doesn't change. We still have a value, we still have a next. So let's take a look at add. Okay. So add is kind of where we have to make the majority of our changes here. The first, we've got this assert statement that's saying that whatever index we pass in has to be greater than 0 and has to be less than the length, right? That's all great. So how does add work? Let's take a look at that. So every time you add, you've got the 1 and then the 0 after. So I guess we didn't really indicate this in our explanation, but this is just 1 is the value and 0 is the index, okay? So in this case, you are adding at the beginning of the list for all three of these. Just a second, it says my internet has been stable. Okay. So then the next piece here is it's saying if index is equal to 0, then this dot start equals new item value, this dot start. Okay, that looks good. But again, we have to make sure we do something to take care of the end variable. So this dot end. So if we were adding to the very beginning of the linked list, index is equal to 0, and we just created a start. And we gave the start a value, and we said that the next variable is this dot start. Then you'd want to do this dot next equals let me actually think about this. This dot start equals a new item, which is going to be the start of the linked list, and we're going to say value this dot start. Uh, but I don't think we'd want this to be the start of the, you wouldn't want the next pointer in the first. So if I were to have an empty linked list and I were to add one to the beginning of the linked list, so index is equal to 0, this dot start is equal to new item with the value being 1, and this dot start would be, yeah, so that's fine. We can make this dot start to be the next value because we're still adding to the beginning of the list. And you would want to put this dot end to be pointing to this dot start. And then remember that this dot end also has so this is assuming that it's an empty list, right? So we need to actually take care of the case where it's an empty list first. So what I'm going to do is add another if statement here that says this dot length equals 0. Okay. And this is just because the case where we have an empty list is slightly different from the case where we don't have an empty list. So I'm going to handle a case where it's an empty list and we're adding something for the first time, right? Adding something for the first time, we want to do this dot start equals new item value. And the next value is this dot start also. So this is because this is the first item in the list, right? First item in the list, so I just want to have the start node. And we want the start node to just point to the start node again, because there's nothing else to point back to. And then we have an end node, right? This is end. And we want the end node to also point to this top start. Yeah, this is just for the case when you have nothing in your linked list. Okay. Okay. So that I think will take care of this first piece of it, the first addition to linked list. And let's see if we can print it out. See if it'll print. Line 35. Oh, my bad. I did not complete this. Okay. So how was this set up originally? Let me just check that. I'm gonna leave this alone. Like this out. Okay. All right. So we have our first number added, right? So now we have a linked list and it's got 1 and now it points to, it should not point to null though. Why does it point to null? I'm going to take this else, make this an if else. Mm. If we're adding 1 and 0, why would it do that? Oh, it's the way that I've implemented this. Okay, we're gonna ignore this print statement for now because the to print is not implemented correctly yet. So let's keep going. All right, so we've handled the case where we can add just one thing at the beginning. So now if we add number 2, now we're no longer gonna be able to meet this condition because the length is now 1. Because at the end of this addition, we have a plus plus, length plus plus. So now we go into this next condition here, else if index is equal to 0. And in this case, you still want to add a new item at the beginning like this. And excuse me. But now you want to set your end value to be your end dot next to be so we have 1 in the linked list, and we can think of it as 1, 2, kind of the end here. I'm gonna say null for now, just for visibility's sake. So 1 points to null, and then we have a new item that we're creating, and we're making a start point to that new item. Now the original item that was there, 1. So we have 2. Now we've added 2 here, but we haven't. We said that 2 next is now 1. And end still points to y, right? So now we want to make sure that end dot next and not end dot next, because the next of the end value must still point to the start, right? So now we're going to do this start. Okay. Anyway, I know it's super confusing. I think sometimes it's a lot easier if you can draw this out and then walk yourself through it. I also think there are many different valid implementations of this that you can do on your own without necessarily following these exact steps. But the ideas are still the same. So just so that I reiterate what I just did is I'm adding a new item to the beginning of the linked list. And the linked list already has one item in it. So the start value of this new value that I added will point back to the original start value. So I added 2, and then 2 dot next will now be 1. And then I'm also making sure that 1 dot next points back to 2. So that's what's happening here in this second line of code. Okay, making progress. So we've added 2, right? So we've got 2 here. Okay, so what else are we missing? Okay, I won't worry about that print statement. When we get to it, we'll worry about it. All right, so the next piece right here is like this big else loop, which handles any cases where you're now adding to the beginning of the loop. So here we're still adding to the beginning of the loop, but let's just see what the behavior is like. So we have 3, 2, and then null, which does not make sense. Okay. I'm going to change this to string because I don't think it's written correctly. Mm. This class. Why is it written like this? Okay. So what I'm going to do is instead of doing this, I'm just going to do a counter I equals to 0. While it's less than this dot line. And then I'm just going to increment I every time. And then I'm going to do buffer item I equals start. Again, this is not what you were asked to do. This is kind of just me fixing the two string method that we have here. I don't think it was incorrectly. So this is the start, and then I'm incrementing this in the root, and then I'm just saying item dot value, and then I equal oops, I need to call it something else. Or val. And we say val.next. Yep, so there we go, fixed it. Now it's working. And this should not say null, it should just say points. Should just print out these. And we're just gonna say that this is the end of this. Start. Okay, cool. Sorry about that. I just had to fix that. Did not look right to me. All right then. Right, so we've fixed the add implementation for this. And it looks like it's working. So you can just assume that this is now pointing back to the beginning. And since both of these print the same thing, you can see that it's a cycle. Great. So any questions on that? I know that was a rough ride there to start off with, but don't worry. Just hang in there. And then there's another similar method that we've got here to print out the cycle n number of times. I'm not going to go through this one because of time, but the solution is at the end, and it is kind of a variation on what I just did here with my two-string method right here. So I've got the two-string method here, and it iterates through this, you know, one time. So how would you do this n number of times? And I think most of you will be able to figure that out kind of quickly. So let's just keep moving and look at the algorithm questions because we only have about 10 minutes left. Yeah, like Jackie's just saying right here, you know, that took some time. They're hard. They're going to be confusing even for STAs, but don't worry about it. This is a hard question. It's designed to make you guys think. Okay, let us take a look at some algorithms practice. Switch gears a little bit. So here's the first question. You've got Mrs. Lovelace. She's trying to line up students for lunch. So she wrote an algorithm to see all possible lines for her and students. What's the runtime here? And a good way to think about that is how many lines will be there. So this is a little bit of a math review, I think. If you have N students, how many different ways are there to organize the N students? Any ideas? You can think maybe permutation combinations, and then from there, think about what the runtime might be. Any ideas? So if you're going through and creating all possible lines for N students, you would be trying to produce N factorial different lines. So the runtime ends up being O of N factorial. So yeah, that's an unusual one. You guys probably haven't seen that very much, but it is there, O of N factorial. And again, when you're looking at code, it will usually be like O of N O1 or O of N squared, but sometimes you'll have something like this pop up. And it's just like a reminder that these things are dependent on the inputs and what the possible outputs are. So this question is about Mr. Babbage, and he's looking for a particular screw in his cabinet, picks up each screw, compares it to all n-1 screws until he's gone through all n screws. So what is the runtime here, and how many comparisons does it need to do? What do you think about this second one? This one I think is a little bit easier. He's picking up one yeah, it's n squared. So he's picking up one screw and comparing it to n other screws, so it's n times n comparison. You can think of this in terms of a for loop also. You probably need to have two for loops, like a nested for loop here in order to make this work. So O of n squared. And then this last one is a little bit more complex. It's about Mr. Ramanjulan. He's looking for a new coat. He doesn't know where his size is on the rack, so he starts in the middle. And because the rack is ordered, if the size he's checking is smaller, he looks to the left. If the size he's looking for is bigger, he looks to the right. And then based off of that, he will kind of narrow down his search space each time. So yeah, it's kind of like a Goldilocks kind of problem. He starts in the middle with code 5. He looks down to find a code that is a little bit smaller, and then based off of that, O n to the n. I don't even know what you guys were asked on the last quiz. Well, it's definitely going to be kind of those, yeah, it's so O of n is going to be anything with the exponent in having like that n at the top is going to be something that's incredibly slow. Okay, so let me see if I can find a diagram that plots this out for you guys. Yeah, here's one good one. Okay, so here is a good plot, right? O to the n. So these are going to be things that are really, really slow. Or not like slow, I guess they just take a long time to do. Because you're now doing so many more operations than if you were doing O to the n. I don't know exactly what you guys were asked on the last quiz. Um, but you're not typically going to see this with most of the coding problems that you guys see in this class. It's going to usually be like O to the n squared. I'll take a look maybe at the end of the class at what the quiz questions were like last week, and um, maybe I can tell you about why they were wrong or why they were right. So just hang on a second there. Okay. So then I'm guessing that you guys also had O of log n also on, let me actually pull up the thing that I just closed. There we go. Right. So in addition to these O n squared and O n and O1, all of these are here. The ones that are like less commonly talked about are O of n log n and O of log n. So these are going to be like decent size time complexities. They're like not too bad. I think once you reach here, you know that you're in a really, really bad place. But then down here and here, I think you're in a decent place. And what these basically indicate, I know these are a little bit more difficult to like visualize, is it's indicating that normally in an O of n time complexity, you're having to do n operations, right? And you're having to make those many comparisons or those many loops or something like that. In the O of n squared case, you're having to make n times n operations, basically. If you see O of log n or O of n log n, you're shrinking down that comparison or looping space in some way. Like you might be splitting the space in half, for example, or you might be sticking to a certain section of your n inputs. That usually indicates that you're no longer seeing the typical n squared or n behavior, and it's actually cutting down on something and shows you like an n log n area. So that's what's happening here, actually. You know that your first instinct in like a search problem might be that you're going to have to search through all n items. But in this case, he's able to cut down on chunk of um, what chunk of the codes that he's looking at based off of some information about the codes. So he's really shrinking that problem space in half every time. And that's the key point here. When you're seeing those kinds of changes in the problem space, you can assume that there is some sort of log involved, right? So that's why this one is O of log n. He's just searching log n times for his time complexity. Now, if we were given a scenario where he didn't know what kind of, like the rack was not ordered, then he would probably have to go through each of these and check them, which is going to be more strenuous, right? So he's going to have to check all of them, all O of n of the codes. So yeah, that is the algorithm analysis practice. Okay. And then there is a final question on maps. Again, I apologize for the poor timing on this. I spent way too much time on the linked list problem, but it was a hard problem, so I felt like it deserved a little bit more time. So this is just a hash map problem, and you're being asked to implement a function that calculates the total for an order. And the orders are kind of you're basically their orders are stored inside of a hash map where the orders are, a key as a string, and the prices are stored as a double. And so we've given you some starter code here on how to work through that. So I think this piece of it will be pretty straightforward. I'm not seeing anybody having trouble with this. This is kind of simple for loop, looping through the map, and adding certain prices to the total price, and then returning that. And then you might have to also implement the hash map, which also should be intuitive at this point. So I won't go through those because of the time constraints again, but I'll really quickly take a look at the quiz from last time and see what kind of questions there were on this. Unfortunately, I can't show you the quiz, but I can still take a look. Yeah. Yeah, I see what you're saying here. It looks like they've got constant time, linear time, polynomial time, and even factorial time on here, but it doesn't look like any of the answer choices, I mean, any of the questions require that you know what 2 to the n is. I mean, so if you're looking at code, there are like obvious ways to realize what kind of time complexity it is. If you have some sort of for loop and you're having to check every single item there, you're probably in for O(n). If you're having some sort of nested loop where you're gonna have to make comparisons where it's n times n, like you like in the screw example that we were looking at before, where this guy has to compare n screws with n other screws, then it's going to be some sort of nested for loop. And then constant time is going to be something like getting and setting, anything in that kind of area. And then we talked about log n and n, which is where you're cutting down on the search space with something else and some other information. So typically you have to go through all 8 quotes. Log n, you only have to look at like maybe half of them. So those are the key areas. And then in the Miss Lovelace example, we also looked at doing O(n) factorial, which is ridiculously huge. Like that would take forever to do. And it's just like you're finding all the possible variations for something, and that's where you know it's a factorial. Anyway, I hope that answered your questions. Hope that was clear what we were trying to do today. Yeah, so awesome. Yeah, I mean, I'll take some sense over no sense. So yeah, I mean, if you still have questions about the quiz, I would definitely say check out the quiz review sessions. I think they do a pretty good job of explaining all this stuff. Yeah, no problem. Happy Friday. Have a good day. Enjoy your weekend. Thanks for stopping by.